My name is Wouter, and it's my pleasure to introduce CrowdNotifier, which has joined the work with my awesome collaborators, Seda, Michael, and Marcel, Kenny, and Kenneth. When this pandemic started more than a year and a half ago, it became very clear that one of the major transmission factors was when people were close by to a COVID positive person, and in particular less than 1.5 meters, and both the academic and industrial community developed very quickly Bluetooth-based proximity apps that would warn people when they had been close so that they could take appropriate precautions, such as get tested or to quarantine. Now, as the pandemic progressed, it turned out that that was not the only transmission factor. And actually turned out that in indoor spaces, the virus would infect people that were much further away than these 1.5 meters. And it is also clear that Bluetooth-based proximity apps don't manage to cover these situations very well because they don't know whether the space is indoor or badly ventilated. So there was a need for another tool. And this type of tool is what this talk is about. So after conversing with contact tracing teams, we realized that the main purpose of this type of tool was to notify everybody that had shared an indoor space with a COVID positive person. And notice that we're actually limiting the purpose here to notification, because it turns out that even though many contact tracing teams and laws mandate collecting much more information, the primary use that this information has is then to call people and to notify them. So we decided to limit the purpose to notification only, thereby, and in addition, by developing a system with strong privacy guarantees, hoping to increase adoption, thereby having the best public health benefits possible. Now, by building a system that notifies people automatically, that would also drastically reduce the load on manual contact tracing teams that have had several points during this pandemic have been completely overwhelmed. And then even in times when they're not overwhelmed, it just takes a lot of time to call people. So the hope is that having a digital system would also encourage much faster notification. Now, building these systems is not without risks. And I'm showing here a couple of risks based on different newspaper articles. The first of those seen here on the right is that data collected for the purpose of this type of contact tracing at restaurants and bars has been used several times already for different purposes, namely either commercial purposes or stalking or harassment of women. Now, a little bit further to the left, both at the top and at the bottom, you see cases where data collected for contact tracing purposes is abused by law enforcement for clearly non-public health related benefits, but rather identifying witnesses or victims or perpetrators of crime, both in Germany and North Korea. And you see in these cases that both data collected at locations as data collected centrally might be suspect to these. And then finally, even though this case is not specific to contact tracing apps, we have seen that any data available on smartphones might enable domestic abusers and intimate partners to increase their coercive control. So therefore, we need to be very careful when deploying systems like this at such a large scale to mitigate these privacy concerns as best as possible. Now, also, and even in many of these examples on the slides, the types of locations that we're talking about are bars and restaurants, but these are definitely not the only ones. And I put here a couple of on the slide to illustrate that the sensitivity of these locations can be much higher. For example, when this is a place of worship or a community center that is then used for, let's say, a political meeting or some kind of activist meeting, or maybe some kind of support group meeting. And so all of this led us to come up with the wide variety of requirements. And I realize this is a bit of a busy slide, so let me just walk you through it one by one. So first of all, on the top left, we wanted to ensure that the system that we build would ensure that generating false notifications is difficult. And this is important both when a notification means that you have to quarantine, because quarantining clearly for 10 days is a very, very impactful event. But even when the notification messages urges people to get tested, that induces a lot of stress. So it is important to build systems that make it actually difficult to generate false notifications. But in most of this talk, I'll be focusing on the privacy properties. And if you look with me at the top left with respect to users, we have seen in the previous examples that we need to protect privacy of visits, both from central servers, from the locations that people visit, but also protect the data that is stored on phones so that we can protect against law enforcement agencies or intimate partners that get access to these devices. Now, with respect to locations, it is clear that especially in the more sensitive locations, knowing that people at this location have been notified can be very stigmatizing. So it is important to protect the privacy of notified locations. And then also, as you noticed on the previous slide, many of these locations and events that happen are actually not necessarily in a public database in the way that bars and restaurants are, and forcing the creation of such a database in order to facilitate the functioning of the system is something that we believe is very undesirable. Now, of course, all of these security and privacy requirements constrain the design space. But at the same time, our goal is to design a system that is usable for users, right? So it requires not a lot of effort, runs on a lot of smartphones, and doesn't require special permissions like GPS and location access that people find very disturbing. And at the same time, for locations, it is very difficult to require locations to deploy special software and hardware. So we wanted to make it as easy as possible to do. And then finally, from our conversations with public health authorities, it became clear that it is important for them to stay in the loop so that they can determine which locations are at high risk. So therefore, people should be notified, let's say not a lot of ventilation, a lot of people, a lot of mingling, versus places where none of these things are the case, in which case maybe it's not even necessary to send a notification. And then finally, to do that in such a way that would scale even when contact tracing teams are under a lot of pressure. Now, in order to design these systems, we came up with a couple of initial design choices. Now, first of all, like essentially any other system in the world that does this, we opted to use static QR codes that are posted by location owners on tables, on entry doors that visitors would scan. But we added a little caveat here that location owners would generate these QR codes locally rather than via a central server. And then users would somehow scan these QR codes with their phone and store a record. And as we'll later see, this actually is an encrypted record on their phone. And then finally, phones will regularly download information from a central server to locally determine whether there is a match and then notify the user. But at no point they will share any of the information that is stored on the phone with anybody, nor share anything in case there is a notification. So this will really drastically limit the attack surface available with respect to violating the privacy of the user. And then, as we said before, right, we don't want to build a system that helps with enforcement of quarantines or enforcement of visitor limits. Now, already by making these design choices, we achieve quite a few of the properties that we set out to achieve. So first of all, with respect to user privacy, right, there is no information at the central server or at any of the locations because everything is stored on the phone. So the first two are checked off. And then because locations generate QR codes locally, there is no need for a database or venue. And then because scanning QR codes with an app is a relatively well-known paradigm to users, we deem this to be pretty easy to use, and it doesn't require any special permission except for camera access, which seems a reasonable thing to do. And then posting a QR code that you print from your browser or whatever does indeed not require any additional hardware and software. So that's good. But now let's zoom into a little bit these remaining requirements, in particular the first one of the user ones. What about the phone? So here we consider an attacker that actually has access to the static QR codes that location posts, because this attacker might come around later, visit that location in order to do a confirmation attack, for example. Now, in the case of notified locations, we actually rule out this attack. And this is not because we want to be facetious, right? But if you think about what is the purpose of these systems, the purpose of these systems is that once you scan this QR code, you will be notified. Now, because the QR codes in our case are static to facilitate usability, obviously an attacker that at some point obtains this QR code can always check themselves in and then determine whether our location has been notified just based on the fact whether that attacker herself gets notified. Okay, so this is a thing that we will. Now, all the other properties that I didn't yet mark as green need to come from the specific design of the system. So let's look at how this system actually works. So during a setup phase, and this is just a one-time event, a location owner will use, let's say, a JavaScript website to generate 2 QR codes. The first QR code will be the entry code that is public, that will be posted at entrances or tables. And this QR code will contain first the description of the venue, lots of name and location, a couple of cryptographic nonces, and most importantly, a master public key for an identity-based encryption scheme. And this master public key is different for every location owner. Okay, so the location owner acts as the trusted party for this particular identity-based encryption scheme. And then the location owner also generates the corresponding tracing code, which is a private QR code that, guess what, contains the corresponding master secret key. And this tracing code will just be kept at a secure location. Okay, now, when a user visits the location, they will scan this QR code, and then their app will show a description of the location and ask the user, do you want to check into the pet's breakout room? And then the user will, yeah, that sounds like a good thing to do. Then at some point later in time, the user will decide, okay, I am done with pet's breakouting, enter in their app, okay, I'm leaving now. And then at that point, the app will create an encrypted record, or rather a set of ciphertexts that capture this specific visit. And the way that works cryptographically is that for every time slot that overlaps with the user's visit, so we typically use hours, but it doesn't really matter, the phone will compute a time and venue specific identity. And you don't necessarily need to parse this complex expression with hash functions, but just notice that it contains the information of the venue, a counter that indicates the time slot, and a couple of nonces to make sure that these cannot be forced. And then once the phone has computed this identity, it will take the master public key from the QR code, the identity, and will encrypt the entry and departure times, and then store this ciphertext only. So no other information except for a bunch of ciphertext is stored for each visit. Now these data stay on the phone and are not shared anymore. Now, in order to facilitate tracing, first of all, health authorities will do as they always do. Interview the index case, namely the person that was positive, and ask, okay, who have you been in contact with and where have you been? And they use this information to determine which locations they would like to send notifications to, or rather to their visitors. Once they have determined this, the health authorities will contact the location owners and say, okay, we need this tracing information from you. The location owner will then use their phone or another device to scan the tracing QR code and upload time slot specific tracing information that corresponds to the time slots that we actually need to send notifications for. And guess what? What is this time specific tracing information? These are the identity-based decryption keys that correspond to these specific time slots. So what does the location owner's device do? It will recompute these identifiers, recompute the decryption keys, and then upload them to the health authorities backend server together with the nonces and the description of the location. And then what the health authorities backend does is to take these, decrypt them, and check, okay, this is indeed corresponding to the location that I wanted to notify, great. And it will then publish only the identities, the identity-based decryption keys, and the time slot corresponding to the actual visit. Now, what does the app do? Well, it takes the identities and decryption keys, does trial decryption on the entries that it stored. If decryption functions, now the app has two things. It has the time slots that, or the actual times that the index case was at this venue. It has the times that the user was at this venue, because that was what was encrypted in the ciphertext. It will compare these, and if there is an overlap, it will notify the user that they need to get tested to quality. And you notice that by only storing these ciphertexts, that hints at you would get privacy with respect to attackers that have access to the phone. Now, it turns out that all of these cases, not too surprising, reduce to properties of the underlying identity-based encryption scheme. What is maybe more surprising is that, like, a generic identity-based encryption scheme does not necessarily make this scheme private. In particular, with respect to privacy of the users, with respect to information stored on the phone, we really need that the ciphertext have identity and trust authority privacy, which is not a property that all identity-based encryption schemes has, but the modified Bonner-Franklin scheme that we use does. Now, with respect to locations, the same thing applies. We need that the decryption keys don't reveal too much information about the location. Now, that is typically also satisfied. And then finally, in order to prevent false notifications, we need a measure of robustness so that decryption will actually properly fail when users should not be notified. So that is as far as privacy is concerned. And then as a result of this system setup, public health authorities remain in the loop and remain able to determine this is a location that we should notify, this is a location that we should not. And because that is the only thing they will do, this will still scale reasonably well and to notify many tens of thousands of users. Now, you might have been wondering, okay, we need to do identity-based encryptions that requires pairings. How well does this scale? So we evaluated this, and we evaluated two different things. So on the first column, you'll see an evaluation that we run on the laptop, essentially to determine how long do these things take for venue owners and for public health authorities. And we wrote this evaluation in JavaScript, and you'll see that, okay, whatever, doesn't really matter. These are tens of milliseconds in the worst case for an operation that doesn't happen very often. So not a problem. Now, for operations that happen on the phone, creating a record, i.e. creating a ciphertext, again, is well below 7 milliseconds, doesn't happen very often, not a problem. So finally, the operation that does happen very often is this trial decryption step. And we see here that it differs a little bit between the first 3 Android phones and the last 2 iPhones. The newer iPhone is much faster than the other ones, but in all cases, timing is below 5 seconds. So we see that we have reasonable performance in all of these cases. Now, just to conclude, CrowdNotifier provides presence notification of location visitors with strong privacy properties because all records are stored encrypted on the phone, and it limits purpose limitation, as well as provides sunset by design. And even though I didn't talk about this much, there are a ton of proofs of security and privacy in the paper. Now, we implemented all of this to show the feasibility, libraries you can find online, and maybe most interesting of all, this system has been deployed into Swiss COVID, which is a Swiss national contact tracing app. It's a slightly simplified version, but I'm very happy about that. Please see the GitHub link if you want to have more information, and I welcome any questions that you might have. Thank you so much.